Myself, Dr. J. Srinivas. I am Assistant Professor in EC Department, B.V. Raj Institute of Technology, Narsapur. Today I am going to discuss antenna subject. There mainly I am going to discuss antenna arrays topic. Okay. First of all, what is antenna arrays? Normally, if you take one antenna, if you take some antenna that may be anything, either it may be isotropic antenna or dipole antenna or horn antenna, anything you take, that is single antenna. But what happens when you want to increase, if you want to increase more gain, or if you want to get more performance, if you want to get more power, in that case normally you need to increase the size of antennas. You need to increase the size of antennas to get more power and more gain. To get more gain or power or electric field, whatever it may be, whatever the performance parameter it may be, if you want to increase, you need to increase the size of antenna. Okay, now this is the main thing you have to do if you want to increase the performance, any performance parameter. Instead of doing this, instead of increasing the size, okay, there is one more way to get more gain, more power, more performance characteristics. That is antenna arrays. Okay, in antenna arrays, normally the number of antennas linear manner. Okay, that means the number of antennas, if you take some isotropic antenna 1, the number of antennas 1, 2, 3, 4, 5, like this, they are arranged in a linear pattern. Then that is called a linear array. Okay, so by taking this linear array, what will happen? What is the resultant performance? That we are going to study in this section. Okay, now by taking normally to get more performance, you need to increase the size of antenna. But instead of doing that, the same antennas, by taking the linear array, linear pattern, we can get more performance. Then what is the resultant performance? What is the resultant electric field? That we are going to study in this section. Okay, in this antenna arrays, our first topic is array of two isotropic sources. First topic is array of two isotropic sources. Array of two isotropic sources. So in this case, first of all, we will discuss only two isotropic sources. Then later section we will discuss n number of sources. But now in this section we are going to discuss about two isotropic sources. So these two isotropic sources, they are placed in the array in the linear manner. That is, both are placed on either side of the origin. This is the origin. Both of them, 1 and 2, are placed on either side of the origin. Okay. Then we will see that we have taken two isotropic sources. These isotropic sources has electric field E0. Okay. Then we have taken such type of isotropic sources 2, and we will see the resultant performance in the direction pi with x-axis. Then the resultant performance we will discuss at a distance of p. What is the resultant performance that we are going to discuss now? Okay. So these 1 and 2 also giving their field in the direction of pi. Then the resultant performance at a far distance pi. At a far distance pi, what is the performance due to these two isotropic sources? Okay. Because of these two isotropic sources, they are placed at a distance of d. So this is d by 2. This is d by 2 from the origin. Okay, both are placed at a distance d by 2 from the origin. Okay. Then the field, electric field due to source 1 is retarded by BD cos pi by 2. So mainly we will discuss that this is there is one more parameter we have to discuss, that is psi we will consider as beta d cos pi. This is one parameter. So it is retarded by psi by 2. Then we will write it as psi by 2 equal to beta d cos pi by 2. Okay now. And electric field due to second source is advanced by psi by 2. That means we can write it as beta d cos pi by 2. One is advanced, one is retarded. So the resultant electric field at a distance p, we can write it as one is retarded and another one is advanced. So we can write E naught. The retarded component we will write as e power j psi by 2, and another one is advanced E naught e power minus j psi by 2. So this is addition of these two, 1 and 2. One is advanced, another one is retarded. Then if you do the calculation, you have to take 2. If you take 2 in the denominator, you can write it here 2 also. You can write 2 here. This is e power plus j psi by 2 plus e power minus j psi by 2. So this one you can write it as, this is 2 e naught. This component you can write it as cos psi by 2. Okay now. Here we know that psi equal to beta d cos pi. Psi equal to beta d cos pi. So you can substitute that one, 2 e naught cos beta d cos pi by 2. Then here we know that beta is phase constant, that is 2 pi by lambda. D, normally if you take lambda by 2 distance, then what is the resultant performance? You can see that is 2 e naught cos 2 pi by lambda into lambda by 2 into cos pi by 2. Lambda get cancelled, 2 get cancelled, so you will get 2 e naught cos pi by 2 cos pi. This is your resultant electric field equation. Okay now. I will take 1 second. Pi by 2. Okay. 2 pi by lambda by 2 get cancelled. Okay. Then this is your resultant field equation at a distance of lambda by 2. Here it is for a distance of d equal to lambda by 2. Okay. Then here we got the equation E equal to 2 e naught cos of pi by 2 cos pi. Okay. Then we will take normalized field component. What is normalized field component? The maximum magnitude. We need to divide the electric field equation with its maximum value. Here the maximum value normally 2 e naught. Okay, because this is 2 e naught the magnitude, and we know that cos the maximum value will come as 1. Then its coefficient it is having 2 e naught. So maximum component is 2 e naught. So we need to divide your field equation with 2 e naught. So it is 2 e naught by 2 e naught into cos pi by 2 cos pi. So this is the equation. With this 2 get cancelled. This is your normalized field component. Cos pi by 2 cos pi. After that, we need to calculate in which direction the field is maximum, in which direction the field is minimum. That is the 2 steps we have to calculate. Then we can draw the radiation pattern for this one. Okay. So to get maximum, And here we have the equation cos of pi by 2 cos pi. So we know that in cos terms, so the bracket value should be equal to, actually in the cos we have got cos of 0 is equal to 1, cos of 90 is equal to 0. So in this, from this we can say that bracket value should be equal to 0 to get maximum value. So here the bracket value is pi by 2 cos pi should be equal to 0. We can write it as, actually this is plus or minus k pi we will write, but k equal to 0 we will substitute. Okay. So this is that whatever the value inside the bracket, that we will consider as 0. Then k equal to 0 we will substitute. Then from this cos pi equal to 0, pi equal to cos inverse 0. This is this in cos 0 will come normally. Cos 0 will come normally at 90 degrees or 270 degrees. Okay, this is angle pi to get maxima. Okay, this is to get maximus, 90 or 270 is coming maximum. And to get minimum, that bracket value should be equal to 90 degrees. 90 degrees means we can write 2k plus 1 into pi by 2. So we can write pi by 2 cos pi is equal to 2k plus 1 into pi by 2. So this k value normally we will substitute 0. Then pi by 2 cos pi is equal to pi by 2. This pi will get cancelled. So pi equal to cos inverse 1. So in for which angles of cos you will get, you normally you have 1, that is 0 degrees or 180 degrees. So this is the minimum values. And we have maximum angles and we have minimum angles. So we can say that this is the radiation pattern. We have maximum in the angle of 90 and 270, and minimum in 0 or 180. So this is minima, or we can also call as nulls. This is maximum lobe or maximum or major lobes. Okay, this is the way we need to find out the resultant electric field of two isotropic sources. See here, if you go back, here two isotropic sources. Here the case we have taken is two isotropic sources is having same magnitude. The case first one is same magnitude and both are having same phase. Okay, this is this is the case of same magnitude and same phase. Now see, all of you see here, we have taken two isotropic sources with the same magnitude E0 and same phase psi, and one is retarded by psi by 2, another one is retarded by advanced by psi by 2. So we have written E0 e power j psi by 2, E0 e power minus j psi by 2. So if you do the equation, you are getting resultant equation like this. There you have substituted beta equal to 2 pi by lambda, d equal to lambda by 2. Then if you substitute these values, you got the resultant equation 2 E0 cos psi by 2 pi by 2 cos pi. Then in this equation you have taken normalized field component. Then we have done substitution for to get maxima and minima. To get maxima bracket value, whatever the cos bracket value is that is equal to 0. Then you got maximum angles 90 and 270. And to get minima, that bracket value should be equal to 2k plus 1 into pi by 2. Then you get minima angles. Then if you substitute that maximum angles and minima angles, you get the radiation pattern like this. Then coming to next one, second case. that is two isotropic sources equal amplitude and opposite phase. That means whatever the sources 1 and 2 we are taking, they are having same field component, same amplitude, equal amplitude, but opposite phase. Okay, they are having opposite phase. Then we are getting the resultant field component in the pi direction. Then at the time that field equation will come like this: E naught e power j psi by 2. This is due to first component. And coming to second component, e power e naught j psi by 2. There we are taking the case both are same amplitude but opposite phase. Opposite phase means here we will take minus. One of the field component we will take opposite phase. Okay, then we will see what will happen. This is E naught, if you take comma, E naught e power j psi by 2 minus e power minus j psi by 2. Here you can take 2j in the bottom, then 2j in the numerator also. Then you will get 2j E naught. This is sin psi by 2. This is bracket where this equation is equal to sin psi by 2. Okay. And also similarly we can take normalized field component by dividing with this coefficient. So then you will get normalized field component is sin psi by 2. Okay. If you have sin psi by 2, then psi value we have to substitute. Psi value is beta d cos pi by 2. So then we have beta equal to 2 pi by lambda, and normally d value we will take lambda by 2. Both distance between them is lambda by 2 we are taking. Then if you substitute these two, that is sin 2 pi by lambda to lambda by 2 cos pi by 2. Then you will get lambda get cancelled, 2 to get cancelled, sin of pi by 2 cos pi. So this is your resultant field equation. This is your resultant field equation. Okay, now for d equal to lambda by 2 distance. If you substitute d value some other value, you will get some other equation. Okay, now then next target is to get maxima, and to get minima. And we know that sin of 0 equal to 0, sin of 90 equal to 1. So this bracket value should be equal to 0 to get minima, bracket value should be equal to 90 to get maxima. So to get maxima means second case, we need to substitute this bracket value equal to 90 degrees. So to get maxima, pi by 2 cos pi is equal to 2k plus 1 into pi by 2. This is we have to substitute. Then we substitute k equal to 0 initial value. If you substitute k equal to 0, equation will come pi by 2 cos pi is equal to pi by 2. Pi by 2 get cancelled. You will get pi equal to cos inverse of 1. So in case of cos, we got 1 in for which angles? We got 1 for 0 or 180. Okay, we got 0 or 180. You will get cos value 1. So you to get maxima, you are getting in angles of 0 or 180. Okay, previous case, if you see, you got maxima in 90 and 270. Now in this case you got maxima in 0 or 180. And to get minima, that bracket value pi by 2 cos pi is equal to plus or minus k pi, because in case of sine you will get my minimum value for 0. 0 means you will take plus or minus k pi. Okay, now then k value you normally you substitute 0, then pi by 2 cos pi equal to 0. That means pi equal to cos inverse of 0. In case of cos, we got 0 for the angles of 90 or 270. Okay, now this is pi minimum. Okay, now so we have maxima for 0 or 180, minima for 0 or 90 or 270. So if you do the relation pattern, it will come like this. Maxima for maxima in 0 or 180, this is maxima or major lobe, and 90 or 270 you will get nulls or minima. Minimum in 90 or 270. Okay. See here, we have taken equal amplitude and opposite phase. So that's why E naught e power j psi by 2, E naught e power minus j psi by 2. But we have taken minus here in between them. Previously we have taken plus, now we have taken minus. Then this is your result normalized field component. Then you have substituted d equal to lambda by 2. Then this is your normalized field component equation. To get maxima and minima, this is the sign equation. That's why to get maxima, you have need to substitute bracket value to 90. To get minima, bracket value should be equal to 0. Okay. Then if you substitute, you are getting maximum for angles of 0 or 180, minima for angles of 90 or 270. Then next case, third case, that is equal amplitude, same two isotropic sources only, two equal amplitude with quadrature in phase. Quadrature in phase means there is pi by 4 phase difference. Pi by 4 phase difference is maintained. Okay, now then same two isotropic sources only, 1, 2, but they are maintaining quadrature in phase. Then the resultant equation will come like this: E equal to E naught e power plus j psi by 2. Here we will add extra component, that is pi by 4, because this quadrature in phase. Then this is plus, we have not told any opposite phase, we have told only quadrature, so we will take plus only here. And then e power minus j psi by 2 plus pi by 4. Here anyway it is minus added already, so no need to take minus here. Okay, now this is minus is coming here, so this is minus pi by 4. It is plus pi by 4. Then the resultant equation will come like this. Okay, here E naught will come because same amplitude. Then take 2 E naught by 2 e power j psi by 2 plus pi by 4 plus e power minus j psi by 2 plus pi by 4. So this equation is normally your cos equation. 2 E naught cos of psi by 2 plus pi by 4. So if you take normalized field component, cos of psi by 2 plus pi by 4. Then you have to substitute psi equal to beta d cos pi. So beta value is 2 pi by lambda, d value is lambda by 2 only. This is cos pi, lambda 2, 2. So this is pi cos pi. We have to substitute this psi value. Then if you substitute this psi value, En is cos of pi cos pi by 2 plus pi by 4. Okay, wait a minute. I just refer once. Okay, this is the right one only. Okay, here it is coming as, you can also write it as pi by 4 plus pi by 2 cos pi. Okay, then the same procedure as a first case to get maxima. This bracket value should be equal to, in case of cos, we will get maxima for the bracket value of 0. That means we will equate to plus or minus k pi. Equal to plus or minus k pi. That is k equal to 0 we will take, that is equal to 0. Then what we will get, pi by 2 cos pi is equal to minus pi by 4. Then pi get cancelled. This is 2. This is cos pi is equal to minus 1 by 2. Pi equal to cos inverse of 1 by 2. This angle normally maximum is coming as 120 degrees or 240. These are not R, this is I. So you are getting maximum in both angles, that is 120 degrees and 240 degrees. So what you will get radiation pattern, you will get like this. You will get maximum in this angle and maximum in this angle. So your radiation pattern will come like this. So you are getting maximum in angle of 120 and 240. Okay, I will draw once again this one. So this is the pattern you are getting with equal amplitude and quadrature in phase. Here we have taken plus pi by 4 due to 1 and minus pi by 4 due to second isotopic antenna. Then we have taken normalized field component. Then we have substituted the condition for maximum. And in minima, if you substitute, you will get 60 and 60 and this is minus 60 degrees. Minus 60 degrees means around 320 degrees you will get. So this is the pattern for equal amplitude and with quadrature in phase. Okay. Then what is the condition if you are using non-isotropic sources? Non-isotropic sources. Okay. Non-isotropic sources. Non-isotropic sources means they are not a isotropic sources. You have taken some other antennas. If you have taken some other antennas, then at that time the resultant field will be f of theta comma pi into f of theta comma pi and of fp of theta comma pi plus fp of theta comma pi. See here, this f value, capital F is nothing but array factor pattern. Means array factor means just now we have taken previous case we have taken this En values. No? These all are called array factor. Okay, these all are called array factor. Okay, now wherever we have taken En, okay, now that is we have dealt with maximum value. Those all are called array factor. So that is array factor pattern. For this one, what is the field? Array pattern pattern. Okay, now then this is fp of theta comma pi, array factor phase. Okay, now so array factor will have some field component that we have discussed in the last three cases, and this f theta comma phi is field pattern due to independent source. Okay, if the antennas having field pattern f of theta comma pi and they are arranged in any one of the case what we have discussed previously, then this is the array field pattern due to that case. If the antennas are placed with the same amplitude and same phase, then first case will come here, and this is the field pattern due to individual component. Okay, now this is F2 theta comma pi is phase due to independent source. Okay, now so this is non-isotropic sources. It means if antennas, if you have taken some other antennas, not isotropic antennas, then this is the f of theta comma pi and fp of theta comma pi, this small fp of theta comma pi, these all are electric field pattern of that sources, and in which pattern they are arranged. If they are arranged in the first pattern, you will take array factor of the first pattern. If they are arranged in the second pattern, you will take the array factor of the second pattern. If they are arranged in like third pattern, you will take array factor of the third one. Okay, now okay, see some examples. Coming to example, you have f of theta comma pi is equal to sine pi. Okay, you have field pattern of independent source. This is independent source pattern. Okay, and the source pattern. Okay, now then these whatever the antennas you have taken, they are arranged same amplitude and same phase. Then what is the array factor? What is the array factor pattern? Array factor pattern is f of theta comma pi is coming as, this is the first case. So first case means cos of psi by 2 cos pi. So this is coming as cos of psi by 2 cos pi. If they are arranged same amplitude, same phase, this is the array factor field pattern. This is the field pattern due to independent source. So then what is the resultant electric field is sin pi into cos of pi by 2 cos pi. If they are arranged like this, then what you will get? This is sin pi. Sin is normally pattern will come like this. Sin is for sin 90 and 270 you will get maximum. So 90, this is 270, and for the first case we got the pattern like this. For the first case we got the pattern like this. So the resultant pattern will be like this. Okay, now if they are arranged same amplitude and opposite phase, then f of theta comma pi will change. F of theta comma pi will come as sin of pi by 2 cos pi. Then what will happen? Resultant field will be E equal to sin pi into sin of pi by 2 cos pi. Then how you will get pattern? This is sin pi pattern into, for sin of psi by 2, this we are getting pattern like this. So your resultant pattern will be like this. Okay, understood this one? Okay. So in the similar manner you can change field pattern, some cos pi. You can do this process once again. Okay, now see here, if f of theta comma pi is cos pi, and if both are same amplitude and same phase, then f of theta comma pi is cos of pi by 2 cos pi. Then your resultant field pattern will be cos pi into cos of pi by 2 cos pi. Then how you will get? Here cos pi is, cos actually we will get maximum for 0 and 180 into, this is first case pattern like this. So resultant will be like this. Okay, instead of this, if same amplitude and opposite phase if you take, this is f of theta comma pi is sine of pi by 2 cos pi, then your resultant field pattern will be cos pi into sine of pi by 2 cos pi. Then you will get field pattern like this. This is cos pi pattern into this is sine pi by 2 cos pi pattern. The resultant will be similar. Okay, like this you will rather pattern multiply. These all are called pattern multiplications. These all are also called as pattern multiplications. Okay, see once again, pattern multiplication means this is normally due to non-isotropic sources. We will discuss. In case of non-isotropic sources, the resultant field equation is equal to small f of theta comma pi into capital F of theta comma pi. This is the addition of two phases. Here small f of theta comma pi is field pattern due to independent sources. This is phase pattern due to independent sources. And capital F of theta comma pi, we will call it as array factor field pattern. Array factor field pattern we have discussed just now. First case, second case, third case. For them we have calculated the En value, normal field component. That is the array factor field pattern. In which manner they are arranged? If they are arranged in the same phase, same amplitude, that is the first case. If they are arranged same amplitude, opposite phase, second case. Same amplitude, quadrature function, that is third case. Depending on that, array factor field pattern will come. Okay, now then if you take independent field pattern is sine pi if you take, and they are arranged same amplitude and same phase, this is the resultant to array factor field pattern will come. Then you multiply both of them like this. Okay, now this is sine pi, this is cos of pi by 2 cos pi. Then resultant field pattern will be coming like this. If they are arranged as opposite phase, now this array factor field pattern will change. Then automatically resultant pattern will be changed. This is also called pattern multiplication. Okay, now coming to next case, we have taken independent field pattern is cos pi. Then this is the resultant field pattern, array factor field pattern due to in which manner they are arranged. If they are arranged in the same amplitude, same phase, this is the resultant array factor field pattern. You multiply both of them, you will get pattern multiplication like this. If same amplitude, opposite phase, now it will come like this. Okay, with this we are going to end the session today. In the next session we are going to discuss n element isotropic sources, then what is the pattern for this one. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.